Hello and welcome to today's AVL Live webinar on tackling xEV thermal management challenges with system simulation. With electrification, the competition to design and manufacture the most efficient powertrain possible is stronger than ever, and there are many hurdles to overcome. In parallel, vehicle thermal management systems get more and more complex. This makes the integration of these systems into the vehicle even more challenging. System simulation is an extremely efficient way to support this process all the way from the concept to the integration phase of development. And today you will hear how. My name is Nadia Siegel and it is my pleasure to be your host today. I work in the Marketing and Communications Department of AVL Advanced Simulation Technologies. I would like to inform you that we are recording this session and the webinar will be placed on avl.com for an on-demand download. But now let me introduce you to the agenda for today. After very briefly presenting AVL and today's expert, Mr. Marko Kolaric, to you, Marko will deep dive into today's exciting topic. He will introduce you to major challenges in the field of vehicle thermal management and discuss why front-loading using advanced simulation solutions will help you tackle many of them and will simplify major development tasks. Marko will present a use case on the thermal management simulation model of a battery electric vehicle to illustrate the theoretical outline. If any questions remain open, we will try to answer as many as possible during the question and answer session after the presentation. Please do post your questions in the chat window in WebEx. You can do this during the entire presentation. But now let's start with a few key facts about AVL. AVL is the world's largest privately owned company for the development, simulation, and testing technology of all kinds of powertrains. It currently employs around 11,000 people worldwide. 65% of them hold an engineering degree. While the headquarters are in Austria, AVL has 30 engineering locations and a customer support network around the globe. 10% of the turnover, which amounted to 1.97 billion euro last year, is invested in in-house R&D. But now it's already time to pass on the microphone to today's presenter, Mr. Marko Kolaric. Marko is a simulation expert with a strong focus on thermal management related topics. He works in customer and R&D projects, performs software testing and validation, and also is an excellent trainer for our software tools. Marko, the floor is yours.
Thank you, Nadia, and a warm welcome from my side as well to everyone who joined the webinar. I hope everyone can hear me loud and clear. And without further ado, I would then like to kick off the webinar. So first of all, let's have a look at some of the challenges in the vehicle thermal management and into the development process. So why is thermal management even significant? Everyone in the webinar understands that the automotive industry is faced with unprecedented legislative challenges in terms of reducing the energy consumption and therefore also the emissions. So thermal management is an effective tool how we can reach those targets, how we can take better care of our environment. It's also quite possible that a vehicle is sold in several different parts of the globe, and of course the thermal management system for a car that is sold to Sweden is probably very different to the thermal management system in a car that you only sell in South Africa or Australia. So we have to keep an eye on the localization of the thermal management system as well. Most of the powertrain components also must operate within a certain temperature band for reasons of safety and durability. Only a durable, safe, and efficient vehicle will make our customers satisfied with their purchase, and they also demand a comfortable vehicle. So HVAC is also an important topic. So what are some of the challenges that we are facing when we are developing a thermal management system? First of all, the components that are part of the powertrain system are very, very complex. This means that most of them have to be analyzed not only in a system level, but also in a component level, which usually requires very complicated experimental setups or very complicated simulation models. This means that in the three-dimensional and testing environment, transient investigations are very difficult or very expensive. Another problem is that a modern powertrain is quite complex. So there are much more systems or many more systems in the vehicle than there used to be 20 years ago. Just compare, for example, a 30-year-old car to a modern hybrid. So the multitude of the systems that we have in the car are, there are much more systems in a modern car. And of course, this means that we have to take care about the integration of these systems. Only a completely and optimally integrated multitude of systems will operate at maximum efficiency, and this means that we have to take care of the integration as early in the development process as possible. Only this way we will end up with a satisfactory result. And last but not least, due to the increased amount of vehicle variants that OEMs are producing nowadays, also the time to market is constantly being reduced. This means that we have to, of course, rely on simulation and perform some of the development already in the virtual environment. Let's have a quick look at the typical thermal development process. So in the first step, we have to come up with a list of requirements. So we have to ask ourselves questions such as, what will the vehicle be used for? So for example, the application of a high performance car and a pickup truck will be severely different. And this also means that we have to define the use cases where the vehicle will be used. So for example, if you're driving at a low velocity, towing a trailer uphill, you will only have a limited amount of cooling air available as compared to a high, for example, for a vehicle that will be used to drive fast around the track. So the boundary conditions here are completely different. We also need to take care of the powertrain topology. So we have to know which components will require active cooling, active heating, and this way we can come up, of course, with a list of components that need cooling, with a list of components that we need to purchase and integrate into our system. And last but not least, we also need to take care of the climate conditions. So we should have in this first step a list of thermal requirements. In the next step, we try to develop a concept of our thermal management system where we evaluate different topologies. So we basically have to come up with a system that fulfills the conditions imposed by us, onto us by the design team. So maybe some concepts would work, but due to packaging issues, you must change them, you must modify them. Here you can also already size the components. So you pretty much will know about the maximum heat rejection that the powertrain will send into the thermal management system. So you can already perform some steady state investigations at the maximum thermal load. And for this, we already usually resort to simulation with one-dimensional steady state simulation models. And here in this step, we can already start with some very basic transient investigations. In any case, after doing this second step, we have some kind of an initial VTMS specification already. So we've picked out our components that we plan on using in the vehicle, and this means that we can move into the virtual validation, where we can already build three-dimensional models of the chosen components. Why do we have to do that? So for example, when we're looking for a radiator that will be used in our vehicle, from the supplier we usually get some kind of performance data that was measured in really an ideal scenario on the test rig. But as soon as you place this radiator into your vehicle, of course, the story will change a bit. There might be some flow obstacles, there might be other heat exchangers in front of it or so. And this means that the performance characteristics you got from the supplier will, of course, be significantly different. And this is a good moment to use 3D component analysis, so 3D simulation, where you can really analyze in more detail how this component would behave in your vehicle. And of course, you can already do some testing in parallel so that you can confirm or maybe even improve your simulation models. And this means that equipped with this data from the experiment and 3D simulations, you can then update the 1D steady state model from the previous step. So you will end up with a very, very well calibrated system simulation model that you can use to confirm your VTMS concept. So you know that even with these components that you've selected here, your VTMS system will be able to keep up with the maximum heat load. And once you have such a model, you can of course move on to develop the controls. So the model is now ready for transient operation, and you can evaluate the behavior of the thermal management system in different driving cycles. And you can then also optimize the control strategy. For example, in a battery electric vehicle, most of the auxiliaries are electrified, which means that you have pretty much free control over the operating mode of them. And for example, you can then figure out when you really need to activate the fan, what's the pump speed you actually require, and you can really then come up with a very good control strategy that will ensure that your powertrain will operate at maximum efficiency. In the end, all of this has to be, of course, validated on the road or in a laboratory, and there will always be a difference between simulation and testing, no matter how small it is, and you can then use this. Last step to fine-tune your control strategy. In case, of course, you see that there is something wrong here, you don't really confirm what you've developed in the simulation world, which of course shouldn't happen but can happen. You, of course, can always revert to a couple of steps back and have a do-over. But the bottom line is that the simulation, at least in these three central and integral steps of the thermal development, is a very good asset. So you can save a lot of time, you can save a lot of money, and most of the development can be front-loaded, so you can perform it much earlier in the development process and you don't have to wait for the prototypes. Next, let's have a look at some types of simulation that are available and that can help us in the thermal development process. So generally, we distinguish between two types of simulation here. The first one being the component simulation. So these are various CFD and FEM codes. They're highly accurate, but since you can see that and everyone understands that we are here really dealing about very complex geometry that require very large meshes, they're very computationally demanding, of course, because of that. And for that reason, one has to be very careful when devising a simulation plan. So most of these components are too complex to be really investigated in transient operation, and in order to have a good coverage of the simulation plan, of course, you need to very carefully define the steady state points that you're planning to investigate. But they are, of course, very suited for detailed component investigations so that you can, for example, identify hotspots in some parts of the components and so on. On the other hand, we have system simulation, which is very tailored for system integration and optimization. So you have a much lesser physical complexity of the models that you use here. This, of course, means they are much faster. Most of them will run under real-time factor 1, so they are faster than real-time, at least in most cases, which means that the simulation times are really much, much shorter than in component simulation. So here you can really run tests that are several hours long, pretty much in one afternoon, or even several scenarios such as that overnight. The drawback here, of course, is that they are less accurate without calibration. By this I mean that in order to get really accurate results, you will have to rely on testing data or on data that you get in the component simulation step. But of course, since we've stressed that integration and optimization is key, this is a very, very useful tool. And in this webinar, I would like to talk you through a use case that we've developed in AVL Cruise-M, which is our system simulation code. And the use case will be addressing a battery electric vehicle VTMS simulation. So if we think of a typical battery electric vehicle nowadays, of course, there are several systems that we need to consider if we want to get a clear overview of the thermal behavior of the vehicle. We have the electric motor, so this is kind of the core component. Of course, it comes with an inverter and also some other power electronics. It's also the battery is a very important component in a battery electric vehicle. And these components, of course, require some kind of cooling. So usually we have liquid cooling, but it could be air cooling. And very typically, this is also assisted by the refrigeration cycle. So we have the air conditioning system, which of course can also assist the cooling. So I'm talking about battery chillers. This can also work as a heat pump, so it's also a very important system that we need to consider in this day and age. Finally, we also have to take care of the cabin in the vehicle model, if nothing else. So maybe if we're not really planning on doing a very detailed HVAC study, we need to at least consider the power load on the refrigeration compressor and other auxiliaries here. So this is also one of the systems that should not be neglected. And in the next slide, I would like to present briefly such a model in Cruise-M. There are too many details in this model, so I will just present some basic interactions and some highlights. But of course, there is a webinar series on the AVL website where some of these systems are explained in more detail that you can look up on the website in case you're interested. So this is one of the installation models we have in Cruise-M, and our users can have a look at it. And let me now guide you through the model quickly. So first of all, we have the powertrain. This is the core of the model. In here we define the drive cycle, we define the driver parameters, we define the transmission ratios and losses, the vehicle dimensions, the wheelbase, and similar things. So this is really the core component. And in it, of course, we also have the electric machine, the battery, and the inverter characterization. We also need to consider the thermal model of the battery. So the battery pack, as we all know, is huge, and also one of the most interesting components when we are talking about thermal investigations in an electrified powertrain. We also have the electric machine thermal model, and we have the inverter thermal model. So all of these systems, so these three, the battery, the electric motor, and the inverter, they are all just lumped masses networks. So they're simplified accumulative models that we use to investigate the heat transfer phenomena in the vehicle. As already mentioned, these components require cooling, and this is done with a cooling circuit. So in here we model the flow of the water glycol mixture, and we also have a subsystem where we consider the air conditioning, and we also calculate the cabin temperature here. At the bottom here we have two components. One is called the boundary conditions, and in this component we basically define the ambient temperature, ambient pressure, ambient humidity. So basically things that provide the ambient conditions, which will of course also have an impact on the thermal behavior of the vehicle. And we have the data router. This is simply a component that we use as some kind of a signal hub that sends informations or signal buses from one subsystem to the other. So I will now briefly present the interactions in the model, some of the basic ones. As already mentioned, in the powertrain, we also have the parameterization of the battery pack characteristic, of the inverter characteristic, and of the electric machine characteristic. And based on the operating point of these components and the temperature of these components, we will receive some kind of a power loss that we can pretty much directly translate into heat loss for, first of all, the battery, then for the electric machine, and also for the inverter. And the thermal models of these components will then calculate the temperature of these components. And this is something that we are sending back to the powertrain model. And these are then the temperatures that are used to determine the battery power loss, the electric machine power loss, and the inverter power loss. So it's kind of a closed loop system here. On the other hand, of course, we need to provide some kind of active cooling to the battery, to the electric machine, and to the inverter. And this is done in the cooling circuit. So the cooling circuit here, we basically only simulate the flow network of the water glycol mixture. Of course, we also have the pumps. We have several different valves modeled, and there is also the cooling package. So the cooling package, as we will see later on, provides cooling of the coolant and also of the oil that is used to cool the electric machine. We also use it to calculate the temperature of the coolant in different parts of the system. And in order to be able to do that, of course, we need to get some kind of a battery cooling power. So this is basically the heat that is exchanged between the thermal model of the battery and the coolant. And we do the same thing for the inverter. We also do a similar thing for the electric machine oil. So this is then cooled by the ambient air here in the cooling circuit as well. I also mentioned that we need to sometimes assist the coolant by cooling it down with the refrigerant, which is done here. So in the air conditioning and cabin subsystems, so we also exchange some heat between the coolant and the refrigerant, of course, based on the heat transfer data that we have for our chiller component. There is also a control system in place for each of those subsystems, and that is used to then control the auxiliaries. So we have, of course, the several pumps in the cooling circuit. So we have the mid-temperature and low-temperature pump. We have a pump for the electric motor oil, and of course we have the air conditioning compressor. And all of these components, of course, provide some kind of a power loss, or maybe not a power loss, but a power draw from the battery. And this is something that we send back to the powertrain system as some kind of an additional electric load. Now, as mentioned, there's not time to go into too much details here, so I would just like to show some details, some highlights of this model. And first, I'd like to present the cooling package. So the cooling package is basically a component that we've developed to allow the user, or to enable the user, to simulate the overlap of various heat exchangers. So this is quite a typical constellation in any type of vehicle, really. Usually you have several overlapping heat exchangers in the front of the vehicle. So you can have, for example, an air conditioning condenser. Then you maybe have some kind of an intercooler, and you also have the main radiator. And this is an assembly that can be modeled in this cooling package component. And the airflow in it can be considered either as a mass flow or as velocity. So you can, if you have some kind of CFD data available of the cooling package, you can simply map the velocity field in the shape of a 2D map. Segmentation is defined by the user. So if we have a look at this image here, when we see these full and dotted lines, so these are various cells in the heat exchanger that you can consider, and you get some average results for each of these segments. But of course, this is arbitrarily definable. We also output 3D results, so you can have a look at that in a more interactive way, which is of course much clearer than simply looking at a bunch of curves for each of these segments. Now this is a feature that is very handy and helps you spot some issues with the design in the concept phase where maybe you don't have any CFD data, or when you're really trying to investigate if what you have in mind would work at all. Of course, you can later parameterize it with actual data that you have, but this is especially useful in the concept phase. I would now maybe give you a short online demo of this component. So here we are in the cooling circuit. This is what I've previously already mentioned. This is where you calculate the flow and temperature of the coolant mixture. And this is then the component. It's part of the cooling system model as mentioned, and you can choose between the mass flow and velocity definition. There's also a neat visualization that helps you understand the heat exchanger. We have the technical drawing that will guide you through the process of parameterizing the components. So you basically have to define the geometry of the heat exchanger, and you need to take care of the friction data for the air and coolant. As mentioned, there are also 3D results, and after the simulation, you can then have a look, for example, at the temperature distribution in the liquid. Okay, so this was a brief overview of the cooling package, and next up, I would like to talk you through the details of the battery pack thermal model. So I've mentioned that we calculate the flow rates of the coolant in the cooling system model. And here, this is the battery pack thermal model. And as you can see, we have a cut here. So this is a boundary component that receives the signal about the coolant flow rate and of course also the coolant temperature from the cooling circuit model. So this is just a boundary condition that we, using the signals that we call data bus connections in CruiseM, we get this from the cooling system. And then this fluid then passes through the battery pack and then returns and exits here. So we have 7 identical battery modules in this battery pack thermal model. And the nice thing in CruiseM is that you only have to do this once. So you can only model one module, and the rest you can simply copy as a link. And if you then apply changes to the first module, this will automatically also be reflected in the rest. And in return to the cooling system, we simply provide the sum of the heat flows that occur between the coolant that is passing through the individual battery modules and the coolant passing through them. So this way we can then calculate the outlet coolant temperature from the battery pack also in the coolant system model. And of course, we also here consider some convective heat transfer to the ambient. Now let's have a look at one of the details of a single battery module. We have, as already mentioned here, the coolant inlet and the coolant outlet. So this is a segment of the cooling plate that applies to a single battery module. And this is then, of course, connected to a segment of the housing. So this is where the cooling actually happens. Also, this battery module, this is also a subsystem. And let's have a look at some of the details here. This is what it looks like inside. On top, we have the bus bars. So this is the battery cell, but I will talk about it a little bit later. On top, we have the bus bars, which is represented by a couple of lumped masses. So these are used to calculate the temperature depending on the sum of all heat flows coming in through the thermal ports. We have the end plates of the battery module here and here. And here on the bottom, we have the heat transfer to the cooling plate. So these are basically the connections that we see here on the left are connected to this part here. So this is This is where most of the cooling of the battery actually happens, as we will also clearly see later on. The battery cells or the battery module, they are represented with a discretized solid, so it's a three-dimensional discretized solid. And I would like to now talk about this component. It's basically a freely definable component that is used to exchange or to simplify the process of building thermal networks of batteries. So imagine you have a battery module that maybe includes dozens of cells, and if you wanted to consider each of the cells or at least groups of cells individually, you would have to basically construct quite a monstrous thermal network consisting out of dozens of solid masses or lumped masses and even more thermal connections. And this component simplifies this process. So it's a component that you can use to, especially geometries such as this one, such as the battery module or a battery cell, you can simply discretize it into several different smaller cells. And these cells will then automatically take care of the heat transfer between them. And the nice thing is that you can freely define the size of these cells. You can arbitrarily define heat ports and heat sources. You can consider insulation, and 3D results can of course also be written. And then you can really get a nice overview of what's happening thermally in the component. So again, I would like to show you an online demo of the component. So that's the component. And again, we have a tech drawing that's helping us understand what it is we're doing. And as mentioned, you can choose different materials. You can even define your own. The cell size can be constant or not. And you can even consider heat contact or heat resistance between the contacts. Arbitrarily, you can define heat ports, measurement points, and external power sources. So these are the heat ports that we have previously defined. You can use them to connect the component. And in the end, we also, of course, get some kind of a 3D result, and we can plot this result for any time step in the transient simulation. And by looking at this green color here, of course, we can clearly see that the cooling plate here is mounted to the bottom of the component, as we've previously already seen. Okay. So that was the discretized solid and the battery modeling approach. And one of the components that also needs to be considered is, of course, the inverter. So here on the left side, we have a simplified 3D model of the inverter. So the component is usually complex enough that a three-dimensional investigation makes sense. But of course, this means that transient investigations are pretty much off the table, or at least very expensive. And if we really want to consider what's happening with the inverter, if it's operating for several hours, we have to come up with a system simulation, so something like we see here on the right. So we have to somehow convert from 3D to 1D, and then we can consider the transient thermal behavior of this vehicle. And we have, for example, here on top, so these are the IGBTs chips. We have the power loss from the powertrain model, and this heat is then spread throughout the system. And here on the bottom, we have the coolant flow rate and temperature from the cooling circuit model. So a similar approach as the one that we had in the battery. So we're receiving signals from the cooling circuit, and of course then we are bringing the heat flow back in order to calculate the outlet temperature of the coolant. And in this model here, we can then get a comprehensive overview of the temperatures in the inverter. Now, of course, you might wonder how you can transition, or what's the easiest way to transition from this model to this model. And with our software solution, it's very easy. We have a feature that's called the thermal network generator, and it allows us to transition from 3D to 1D or 0D physics-based modeling pretty much automatically. So considering there is already a three-dimensional model available, you can use AVL FireM. So this is our CFD code. You can use it to perform a thermal investigation of the component in question. You can perform or at least choose different selections in the FireM. And each of those, so these are certain parts of the geometry. You can specify also the heat transfer connections between several parts of the component, and FireM will then automatically identify these components, connections, and also material properties. And here I'm talking also about, for example, the coolant flow rate, about the initial temperatures, the material properties, and so on. And it will then automatically, it really takes only a couple of clicks, generate a data exchange file that you can then automatically import into XEV and generate such a model. So most of this process is automated, and the model you end up with will be calibrated. This means that it will give pretty much the same results as the one that Fire will give. So of course there will be some discrepancies, but they're very, very small. Again, I would like to show this, or the simplicity of this solution, in an online demo. So here we are in FireM, where we can activate the generation of this file by simply loading the global formula. And after the simulation is completed, based on the available results, we will generate the previously mentioned file. And in XEV then, by using the thermal network generator, we can simply load this file. And you can inspect what's being imported, so the liquid properties, the solid properties. You can, for example, add arbitrary heat flow sources, change the material, or change the mass of the component. You can also inspect heat transfer data and even change it. And after clicking on Run, the model will then appear within a couple of seconds. And this is then the model that you can pretty much use and integrate into the system simulation model. So in the system simulation model, what are some of the results that we end up with? Of course, once we've constructed such a model, we want to have a look at some of the results and the thermal behavior of the model. First of all, you want to make sure that the vehicle is actually doing what you want it to do, so it makes sense to perform the vehicle velocity analysis. And we can see we follow neatly the WLTC highway profile here. And if we have a look at the battery state of charge here, we'll see that also our recuperation system is working quite nicely. So if we have a look here at this point at about 300 seconds, we can see that the vehicle starts to brake. So this is clearly here we also have some energy recuperation, and the battery is then slightly recharged. And something similar happens here at the end of the cycle, where we have a long braking phase, and we can again see an increase in the battery state of charge. Of course, we're also very interested in such a model where we are trying to have a look at the energy consumption of the vehicle and the power draw of the auxiliary. So of course we can have a look at the current that is drawn from the battery by the 400 volt auxiliaries. So this is the red curve, and the 48 volt auxiliaries. This is represented by the blue curve here. So I'll explain in the next slide why this chart is slowly dropping. And of course, our main heat source for the thermal management system are, of course, the battery and the electric machine. And we can have a look at the power loss of both of these components as well. And we can see, of course, that the electric machine, so the power loss, it pretty much corresponds. So the peak power losses here pretty much corresponds to the acceleration phases that occur in the drive cycle. We can also have a look at, for example, the cabin temperature. And as we can see, we've started on a pretty hot day. So the initial ambient condition is 35 degrees Celsius. In the cabin, this is even a bit more. So we start off with 42 and something degrees Celsius. And we can see that once the air conditioning starts to work, It'll take us about 5 minutes or 300 seconds to reach the set cabin temperature. And we can also have a look at the compressor speed. And notice how the cabin temperature is dropping, also the compressor speed will drop. So after about 300 seconds, we're only maintaining the current state. We're not really investing too much power into the cabin cooling. And we can see that the compressor speed is also slowly dropping. And this is also the reason why in the previous slide, the current of the 400 volt auxiliaries was dropping as well. We can, for example, also have a look at the coolant temperature in the battery pack. So if we have a look at this chart here in the upper left, when the coolant enters the battery pack, we can see it's at about 23 degrees Celsius, and it's heated by about 4 to 5 degrees Celsius when it exits the battery pack. And this is all calculated in the battery thermal model that I've previously shown you. We can also have a look at the chiller coolant temperature. So in the battery pack, the coolant is of course warmed up, and this is the temperature that it has when it enters the chiller. And in the chiller, it is of course chilled, as the name suggests, and it exits with about 23 degrees Celsius. So these are just some of the results that we can observe in such a model, in addition to the ones shown in the online demos. So this slowly brings us to the end of this webinar, and I would like to wrap things up with a summary. We can all agree that thermal management is a key topic in vehicle development, and especially in xEVs, optimal integration of all of the systems on board the vehicle is especially crucial. And supported by simulation tools, the integration process can be started already in the concept phase. And AVL simulation solutions, of course, simplify the consideration of some powertrain components in the system simulation. So you no longer have to lean on experimental data and 3D data. You have components that assist you in performing such investigations, such as the demonstrated cooling package, the discretized 3D solid that you can use especially for the battery or some other similar components where you are dealing with a large thermal mass. And we also have the automated 3D to 1D transition. So this is especially handy when you have already three-dimensional models of your components available. And all of these solutions together, for example, with our 3D code, so with FireM, not only system simulation solutions, they're available as one package called the AVL E-Suite. So this is really something that you should look into if this webinar was interesting for you. So I would like to thank you for your time, thank you for your attention, but before we say goodbye, I would like to open the floor for questions. So if there are any questions, or if there were any questions during the webinar, I would like to now invite Nadia to ask them, and we will discuss them.
Thank you very much, Marco. And here they come. We already received a few questions. Thank you very much for those. It is still possible to ask your questions, of course, in the chat window of your WebEx application. But Marco, if you are ready, let us start right away with the first one.
Yeah, let's go.
Are fuel cell vehicles supported?
Yes, of course. So we are also aware that fuel cell is one of the technologies that will define the future of mobility. So we are constantly working on improving our solution. So you can consider the fuel cell in multiple scales, really. So it can be a Kulikowski model, or we're also working on developing and improving our physical fuel cell model. And you can also, of course, consider then the fuel cell on a very rudimentary level in the vehicle system, or you can go into a full-blown balance of plant model as well, together with thermal management systems and so on. So don't be afraid, this is very much supported.
Perfect. Thank you. Was the HVB thermal model that you showed in your use case, was it developed in Fire M?
This specific one, no. But of course, this is also something that we can do. Last year, I did a webinar on the subject. It was pretty much similar to what I've shown for the inverter today. So there was a Fire M model of the battery module, and we used this automated 3D to 1D transition. And we came up with a thermal model of a single battery module, and we then constructed the whole pack out of that. So I think we had 36 battery modules. And this is available in one of the webinars. I'm not sure, Nadia, now maybe what's the best solution to provide the link to this webinar, but maybe we can send an email to whoever asks this question later with the link. But in this specific webinar from today, the battery module is simply developed or constructed in CruiseM. So this is by using the discretized 3D solid that comes as a standard part of the CruiseM thermal library. But of course you can combine the two approaches. It's also possible.
That's one of the very, very cool things about the solution we are offering, of course. All of the webinars we showed in the past are available on avl.com/webinars. And you can pick and choose the on-demand versions of them, to answer your question, Marco. Next question, what kind of coolant did you use in your use case? Was it water?
It was a mixture of water and glycol. So it was a 50-50 ratio, I think.
Okay, thank you. I messed up with my unmute button, sorry about that. We received some questions about the openness of CruiseM. So that one comment was that the 3D to 1D, 0D extraction is great. And does it generate a functional mock-up to be used in another software, for example?
Yes, CruiseM is completely FMI standard compliant. So once you have a model in CruiseM, the only thing that you need to do is simply define the input and output channels. And you can then, of course, generate an FMU unit. And you can then use it in any other tool that is compliant with the standard. So this clearly works. And also the other way, you can also import third-party solutions into CruiseM. There's really no limitation to that.
Okay, thank you, Marco. Then a very technical question. You showed in the battery SOC graph in the x-axis, the 300 value was the regenerative braking applied. So does your model consider that too?
To be honest, I'm not sure because I didn't do the powertrain model, but I would imagine yes, because it's based on a real-life project that we did a while ago. So for sure, this is considered.
Perfect. Regarding the discretized module in the battery modeling, a battery module is composed by many cells, so it is not heterogeneous or completely solid. So A, is a solid block approach accurate enough? And does it B, but maybe you want to answer that one first?
Sorry?
The question goes on. How difficult is it to parameterize this model using data from the cell battery supplier? So, is a solid block approach accurate enough, was the first question.
I would say yes, it is accurate enough, at least for this thermal part. Of course, all of the cells don't have to be of the same size. We have to clarify this. So if you think there are some hot zones or something like that where you will really experience a different behavior of the battery cells, this can, of course, be considered. So they don't have to be of the same size. They will, of course, have different properties. They don't have to even be of the same material. What I have to stress is that if you are working with this discretized solid, everything will just be called solid, but you can define, for example, completely arbitrarily the material properties of different cells or different segments of the module. And these properties can, of course, be for some jelly roll or something like that. It doesn't matter. So it's only called a solid in the GUI, but you have complete freedom over how the material behaves or something like that. Now, of course, you won't be able to consider some flow phenomena that might occur inside of it. It will be treated as a solid, but at least to calculate the temperature and to get an idea of the thermal behavior, in my opinion, it's good enough. But here also I have to stress that what I've shown with the discretized thermal solid, this only applies to the thermal part of the battery. If you want to consider the changes of this in the electrical part of the battery, there is also an electric counterpart of the battery component where you actually consider the electrochemical properties of the battery. And if you want to experience different effects or different behaviors of individual cells based on their temperature, you will need to model as many electrical or electrochemical battery cells as you did the thermal part. So for example, if you discretize your battery module to 15 segments, you will also need to model 15 electric battery components. So here we have to distinguish between what we're modeling in the thermal part of the model and what we're modeling in the electrical part of the model. And to get to the second part of the question, the parameterization of the battery cell, there is a tool available in FireM and CruiseM. It's called the battery parameterization wizard that allows you to import pretty much out of the box the supplier or test data for the battery, and it automatically fits the parameters to capture the also the transient behavior of these batteries. So this is quite a complicated topic, and it's maybe not the focus of this webinar, but there are, of course, solutions in place to simplify this process.
There's another question about the discretization, maybe very, very brief answer on that one. Regarding the discretized 3D cells, can we consider them as a kind of mesh? And in that case, is it helpful to make a discretization sensitivity analysis in CruiseM?
Yeah, of course, when you specify the size of the cells, you inevitably create some kind of a mesh. So of course, it's not a. I'm not sure where the limit is with this solution, but of course, it does make sense to come up with a very, very fine mesh, but at least for a coarse mesh where you have, I don't know, maybe 100 cells to consider, then yeah. And if you also want to consider a sensibility analysis, I think that makes sense because some parts of the battery module are, for example, closer to the cooling channel, some are closer to its neighboring module, and some are really maybe exposed to the ambient or something like that. It does definitely make sense to perform a sensitivity analysis of how different meshes would behave, or how different discretization levels would behave.
Okay. Now a very general question to breathe. Are any tutorials or reference models available in CruiseM?
Yeah, we have quite an extensive list of installation examples. So I think there's about 200 of them now for different applications. Also, the model that I've shown today is pretty much an installation model that you can have a look at. I only did some small modifications for the webinar, but principally the model is there. It is also documented. And we also have some chosen models that come with our installation that are really extensively documented. So they are called primer models, and they really come with 30 pages of documentation. So you can really take CruiseM, you can print the manual, and you can start working your way through the process of setting up also very complicated models. So these are just some selected models, but of course, in general, we do aim to provide some guidance to our users. And there are also, for each feature that we have There is also a very simple installation model where you can use to learn how the feature operates. You can start to understand the logic behind it and then apply it in your own modeling.
Thank you, Marco. Someone is saying I'm currently working on an immersion cooling battery thermal and fluid behavior analysis project. And he wants to know what the best way is to get HTC, so heat transfer capacities. The person also adds that he really likes, like many people do, of course, the automatic option to get a model by connecting Fire to Cruise M. So maybe you can briefly give a brief answer to that one, but not too detailed, maybe.
Yeah, so my background is pretty much in system simulation, and to be honest, this sounds more like a CFD problem to me. I do, of course, appreciate the problem that you are facing with this. To get the HTCs, I think you pretty much have to perform a very detailed CFD analysis, and then you could perform this automated transition from 3D to 1D, and of course the HTCs that were calculated in FireM, so in CFD code, would automatically be transferred also to Cruise M. So this is maybe one way to get or to come up with these HTCs.
And to get in contact if you need detailed deep dive information after the webinar.
Yes, of course.
Another question,
We're happy
Marco.
to answer questions.
Right. Can heat pumps be modeled?
Sorry?
Can heat pumps be modeled?
Yes, of course. We have a library of two-phase flow components, and we support pretty much any application from air conditioning, heat pumps, waste heat recovery, so the Rankine cycle. And yeah, so this is obviously supported.
Perfect. And another very interesting question about the immediate future. What further developments are planned in that solution?
Okay, so in our upcoming release, we are aiming to provide, or we will provide, a very neat solution that's called the battery module. It's basically an extension of the discretized 3D solid that I've shown today. Users will be able to also parameterize the battery electrically. Not only I've shown here the thermal parameterization, but that component will also provide the option to parameterize the component electrically. You'll have the option to additionally, in the same component, specify, for example, also the cooling plates, the end plates, and very importantly, we also have a partnership with Batemo, who are a provider of battery cell data. So we will also be, they provide battery cell data, battery cell models, and you will also be able to out of the box consider some popular cells that are available on the market and investigate how they would behave in thermally and also electrically in your battery pack constellation. And of course, you will also be able to customize this battery. So this is maybe one of the interesting developments in the immediate future.
I think this was the perfect question to end this webinar, since time is already up. We received some more questions and will of course answer those directly to you via email. But as I said, time is up, and I would like to end this webinar at this point. To find out more on this topic and many other exciting topics, of course, please visit avl.com. As I said, all our on-demand webinars are available on avl.com/webinars. If you have any further questions that remain open, feel free to contact us via email at asdmarketing@avl.com. Marco and I would like to thank you all for participating in today's session, for asking so many interesting questions. And we do look forward to welcoming you again soon at one of AVL's live webinars. Thank you very much. Have a great day, and bye-bye.
Thank you and goodbye.